Hello, I'm Mike McCulloch. Today I'd like to talk to you about Proxima Centauri in the Alpha Centauri system, which is one of the best proofs of quantized inertia. And it's very neat as well because it's our closest neighbor in space. So this system, called Alpha Centauri, is composed of three stars. So the two central stars, Alpha and Beta Centauri, orbit each other about 30 AUs apart, fairly fast, and they're similar to the Sun in mass. But there's a third star called Proxima, which orbits much further out, about 15,000 AU, and it's much smaller as well. It's only about a tenth the mass of the Sun, and it's a red dwarf. And the interesting thing about this system is the Proxima orbits far too fast to be bound. It's orbiting at about 500 meters per second, orbiting A and B, Alpha and Beta, at 500 meters per second. And so, given the centrifugal forces, it should be zooming off into outer space. But everything about the system tells us that it's actually bound, because the chemistry of the three stars is similar, and also they're co-moving in the sky. So they're probably bound. But physics says that they can't be. They can't be bound. So this is an ideal opportunity to test quantized inertia, especially because things like dark matter can't be used to explain this. So you might say, okay, why don't you just pack a lot of dark matter into the system and then make that agree? Well, you can't. It turns out you can't do that. For instance, increasing, what they have tried to do is increase the mass of the central stars A and B to accommodate to bind Proxima. But they found that they need to increase their mass by 3 times the uncertainty of their masses to do that. So that's not an option. They can't pack dark matter into the system because in order to stay out at the edge of galaxies where they need it to bind the galaxies together, that means that it must have the proposed dark matter must have some sort of physics that keeps it spread out. So you can't then turn around and suddenly bung it into a small system like this. Well, you could, but it's becoming increasingly ridiculous. Also, modified Newtonian dynamics, cannot also be used, can't be used in this system because of its external field effect. So in MOND, the acceleration that matters is the total acceleration of all the surrounding stuff. So the Alpha Centauri system is still within the central part of the galaxy, well, sort of the middle of it. So that means that the accelerations are still relatively high, so the effective MOND would be fairly light. But the interesting thing about quantized inertia is that the acceleration used should only depend on the mutual acceleration between the masses that you're talking about. In other words, the acceleration is within the system. So quantized inertia can be applied here. And it turns out that when you do, then you see it's very much like a wide binary system. The outer star, Proxima, the one that's orbiting distantly from the other two, has a very low acceleration. And this means that some of the Unruh waves that form its inertia are going to be damped by the cosmic horizon. So quantized inertia predicts that its inertial mass, Proxima's inertial mass, should be slightly less than we expect. So the centrifugal force should be slightly less than we expect. And that means that if you model it with quantized inertia, you get a bound system. So this is a great crucial experiment because it shows that only quantized inertia can save this system. You can't increase the masses of the two central stars. You can't use dark matter. You can't use MOND. And yet you have this discrepancy between the orbit and the chemistry and the co-moving character of these three stars. So it has to be quantized inertia. Okay, so I hope you've enjoyed this short, and I look forward to seeing you next time. Goodbye.